Hi, everyone. Hello. So we are going to start our first oral session of the conference. Each speaker will have 20 minutes, and then we'll have questions for 4 minutes, or 3 minutes, and then 1 minute for changing. And then we'll have five amazing talks. So the first, oops. Okay, I have to. So the first talk is by Mengjing, and it's on functional Wasserstein bridge inference for Bayesian deep learning.
Hi, good morning, everyone. I'm Junyu. I'm a third-year PhD candidate from the University of Technology, Sydney. Today, I'm very honored to present our research work titled Functional Wasserstein Bridge Inference for Bayesian Deep Learning. And this is a collaborative effort, so I'd like to acknowledge my co-author, Dr. Junyu and Professor Jie Lu. And this project focuses on the powerful function-based variational inference method based on our proposed Wasserstein bridge for Bayesian deep learning. Here's the content of today's talk. Let's begin with the background. Bayesian deep learning, BDL, is an emerging field that combines the strong predictive performance of deep learning with the principled uncertainty estimation of Bayesian inference. Bayesian neural networks, BNN, as shown in this right figure, all network weights in BNN are random variables represented by the probability distributions rather than the single and fixed value as in these non-neural networks. BDL has been recognized as an effective tool for a wide range of tasks, such as the medical diagnosis, astrophysics, and uncertainty formulation in some tasks. Look at this 1D toy example, which provides good visualization for the uncertainty quantification by using BNN. The black line represents the predictive mean, and the blue shaded arrows correspond to the predictive standard deviation. We can see that compared with the middle region with red training points, the left and the right side without training data have significantly higher predictive uncertainty. Even though impressive progress has been made, the application of BDL has not achieved outstanding performance in some tasks compared with their non-Bayesian counterparts. And this phenomenon can probably be attributed to at least 2 unresolved issues in the parameter space inference. Firstly, it is difficult to incorporate meaningful Fourier information by the widely used IID Gaussian Fouriers for the random network parameters, and they are not always applicable. Consider this toy example. We show the sample functions of fully connected BNN with 2, 4, and 8 layers, respectively, by placing Gaussian Fouriers for the random network weights. We can see that as the depth is increased, the samples tend to form the straight horizontal lines, which is well-known patronage stemming from increasing model steps. And secondly, the effects of the given Fouriers on the posterior inference are unclear and hard to control, owing to the complex model architecture and nonlinearities. So to avoid those issues, there has been increasing attention to performing Bayesian inference in function space instead of the parameter space. In such an inference framework, the probability, the distributions of the random function mapping defined by our BDL models are treated as probability measures defined in the function space. And then the variational objective is defined in terms of the distributions over functions directly. Then one can take advantage of more informative stochastic process proofs, such as the classic GP proofs, which could easily encode prior knowledge about the potential functions, such as the smoothness, shape, and periodicity through the corresponding kernel functions. So in this part, I will briefly review the parameter space and the function space variational inference before introducing our proposed new method. We know that BDL models are usually trained with Bayesian inference by placing prior distributions for the random model parameters, such as that P0 of W can denote the prior distributions for the random network weights in the BNN. The variational goal is to fit an approximate posterior distribution Q of W parameterized by theta Q from the tractable variational family by minimizing the KL divergence between it and the true posterior, which is equivalent to maximizing the evidence lower bound elbow, as shown in this equation 1. Similarly, suppose that P0 of F is the prior distribution for the random function mappings, then like the definition of the variational inference in parameter space, the variational inference in function space can be denoted by this functional elbow shown in this equation 2, where the Q of F is the variational posterior over functions induced by the variational posterior over parameters, and then one can effectively incorporate meaningful prior information via this functional prior P0 of F in this KL term during the optimization. However, for the estimation of this functional elbow, there are 3 issues that need to be carefully considered. The first one concerns the validity of the variational objectives definition. Notice that the KL divergence between the distributions over infinite dimensional functions may be infinite, which will need to yield-define the variational objective. For example, the KL divergence for the distributions over functions generated from 2 BNN with different network structure can be infinite. And the second problem is the implicit probability density functions or probability measures for Q of F and the P0 of F. We know that the explicit PDF for some stochastic process are intractable, such as that for a BN or for some nonlinear functions. And the second problem is the effective and efficient way to estimate the KL divergence between 2 stochastic process, which is equivalent to the supermom over the supermom of all of KL divergence over all marginal finite measurement set. But unfortunately, there is no analytic way to obtain such a supermom in practical optimization. So in this part, I will introduce our new proposed functional variational inference method using the new built Watson bridge as the dissimilarity measure for distributions based on the Watson distance, which can avoid the limitation of KL divergence for distributions over functions. And let's begin with the notations. Suppose that G is a random latent function parameterized by WB, like the definition of variational posterior over functions. Like the definition of the variational posterior over functions Q of F induced by the variational posterior over parameters Q of W. We denote that P of G parameterized by theta B is a bridging distribution over functions induced by the bridging distribution over parameters P of WB. And this is the definition of the Watson distance, which is now well-defined distance metric for probability measures, satisfying the non-negativity, symmetry, and triangle non-equality. We first propose two-step versional inference by the bridging distribution and the functional plural. In the first step, we distilling the functional plural, such as the GP plural, into the bridging distribution over functions by minimizing the one Watson distance between the P of G and the P0 of F. Specifically, we solve such functional one Watson distance on a finite randomly sampled measurement set XM, where the G of XM and F of XM are the corresponding function values evaluated at XM. And this is the dual form of the one Watson distance. We can say that this computation procedure is based entirely on sampling, so it can still be performed smoothly even without the closed form of P of G. And at the same time, we can obtain the optimal bridging distribution over parameters, and denoted by this P of WB theta B star. And once such optimal theta B star is obtained, in the second step, we freeze it and use this optimal P of WB in the regularization term of this elbow to the versional posterior over parameters. And well, this W2 denotes the two Watson distance. Suppose that Q of W and P of WB are two Gaussians. Such two Watson distance can solve analytically. Where this mu Q, mu B, and sigma Q, sigma D are the respective mean and covariance matrix for the Q of W and P of WB. However, due to the isotropy of the one Watson distance, there will be an infinite number of candidate P of WB theta B star with the exactly same distance to the given functional plural. And FBI VI just we call this two-step variational inference method functional plural induced variational inference of FPI VI. Due to the isotropy of the one Watson distance, there will be an infinite number of candidates P of WB theta B star with the exactly same distance to the given GP plural. And the FBI VI just randomly picks one from all the candidates in the first distilling step. And such randomness brings large fluctuation to the following inference process. We illustrate such suboptimal FPI where I use this 1D toy example. Specifically, we use the one Watson distance as the loss to find the three P of WB theta B star with the same and preset distance to the given GP plural. And we run the second step of the FPI VI using that 3P of WB theta B star. And the results are shown in this finger A, B, and C. We can see that even though we can say that the performances of that three models are significantly different, even though their bridging distributions all have the same distance to the given GP plural, which indicates that the first step of FPI VI is with large fluctuations, which may harm the final posterior inference. So to avoid these issues, we further treat theta B in this bridging distribution as the parameters that need to be jointly optimized with the versional posterior parameter theta Q. Specifically, we build a Watson bridge to decompose the intractable distance between the Q of F and P0 of F into parameter space 2 Wilson distance and a function space 1 Wilson distance at the same time during the optimization based on the Bayesian distribution to obtain a more robust solution. Based on this proposed Wilson bridge, we propose a new variational objective in function space called the functional Wilson bridge inference FWBI to obtain the optimal theta Q star and theta B star. And we proved that the variational objective of FWBI is not lower bound of the model evidence, which indicates it is not well-defined variational objective for Bayesian inference. Even though the 1 Wilson distance used in the Wilson bridge of FWBI can link the functional prior and the bridging distribution, we found that it is weak on the higher order moment matching in practice to preserve the uncertainty encoded in the functional prior. We further proposed this enhanced version of the 1 Wilson distance with an additional second order moment matching term denoted by this M2, and we use it in the FWBI in practice. And finally, once the optimal theta Q star is obtained, the posterior predictive distribution can be obtained by this integration process, and we can use Monte Carlo estimation for it. So let's conclude the main advantage of our proposed FWBI. Firstly, it can incorporate more meaningful prior information into the posterior inference compared with the mean field parameter space variational inference, which usually use the IID Gaussian priors for the random model parameters. And it uses the well-defined Wilson bridge to regularize the parameters of posterior of variational posterior with the functional prior, which can avoid the limitation of the KL divergence used in the most existing function space variational inference methods. And moreover, it can quantify uncertainty more accurately using the second order moment matching term in this enhanced 1 Wilson distance. So for the experiment, we evaluate the predictive performance and uncertainty formulation of FWBI for several tasks. The first one is the 1D toy extrapolation example. We compared with the benchmark parameter space variational inference method BBB, denoted by this KLBBB, and is 2 Wilson distance version denoted by this WBBB. And we also compared with the function space variational inference method FBNN, and for and we use the same GP prior for all functional methods with 3 different kernel functions. We can see that compared with the other method, our FWBI can shows stronger capability to recover the main polynomial characteristics in the observation range. And it can provide more accurate uncertainty estimation in these 3 unseen region with appropriate RBF and Merton kernel GP prior. And we also evaluate FWBI for the multivariate regression tasks on 6 UCI data sets. And we show the average results of RMSE. We can see that our FWBI significantly outperforms all other parameter space and the function space variational inference method. And we also evaluate the ability of FWBI to guide extrapolation in the contextual bandit. And we show the cumulative regrets for 3 different reward patterns. The NOR represents better performance, which indicates that our FWBI can provide reliable uncertainty estimation in these decision-making scenarios. And finally, we evaluate the scalability of FWBI for this image classification task. We can see that compared with our FWBI can consistently outperforms all other baselines for the accuracy, classification accuracy, and it performs competitively in the OD detection. So here's the main reference of this work. Thank you.
Okay, so we have time for questions from the audience or online. Yes, there's a question.
Thank you for the presentation. So the one thing maybe a bit of a general question, and something I didn't quite get in the presentation is how do you construct the prior, and especially, I think you made that argument that the functional prior is more interpretable. So for the given applications that you looked at,
Yes.
how did you construct that functional prior, and in what ways was it more interpretable than directly putting a prior in words?
Okay, thank you for your very nice question. For the functional prior, we usually, for the unknown tasks, there are two candidate options for the choosing of the functional prior. The first one, if we have no prior knowledge about the tasks or functions, we can use just a norm, apply a GP prior with RBF kernel. For example, the RBF kernel just for smoothing, and this is non-meaningful prior. So we can reduce the weight of this KL term for the regularization, or we also can use composited kernel function, which by various different kinds of kernel functions, such as the RBF kernel, periodical kernel, or the linear kernel. They are a composition kernel, and this can cover the functional forms as many as possible using this composition kernel.
Great, thank you. Thank you so much.
Any other questions? Yes, there is one at the back.
Thank you for the interesting presentation. I'm not entirely sure I managed to catch all the details, but my question is that to me it feels like, so what you're doing is like in one part, you basically have this distillation part, which is sort of like similar to what Maurizio used to do, where he's trying to learn a better prior for Bayesian neural networks based on some functional priors.
Yeah.
And then you're replacing basically the KL term, your regularization term with the Wasserstein distance term, and then you have your bridge term in addition.
Yeah.
And I was wondering how important is that bridge part in there, sort of in terms of the performance?
Oh, okay. With this bridging distribution, could link the intractable functional distance between the we say the variational posterior over functions and the functional prior. We know that the KL divergence commonly used in the existing function space variational inference. This KL divergence are intractable for many stochastic process, such as we have now BNN posterior and with GP functional prior. Such KL divergence are intractable, and we built the Watson bridge based on the bridging distribution, which could link this intractable distance between this variational posterior over functions and the functional prior. Yeah.
Okay, let's take Mujin again, and I will go to the next speaker. Thank you.
I think.
So our next talk is virtual, will be presented by Deng. Wei, can you unmute and start?
Yeah, you can hear me now, right?
Yes. Go ahead.
Great. Thanks for the kind of introduction, and hi everyone. I hope you have a great time at UAI. So sorry, I was having visa issues, so I cannot attend in person. So today's talk is Reflected Schrödinger Bridge for Constraint Generative Modeling. This is the joint work with Yu, Nicole, Hengrong, Qi, and Ricky. So the background is we want to do generative modeling in constraint settings. And real-world data, such as pixel values in images, often exhibit bounded support. And a common practice is to use the ad hoc stress holding techniques to get the sampling process toward the intended domain of simple structures. So this is fairly popular. However, it's still not implemented in a principal framework. To make it more general, the reflected diffusion model studied the constraint score matching using the explicit training loss and the reflected Brownian motion. So it turns out that this method is fairly scalable. However, it may not easily adapt to diverse domains if we cannot derive proper diffeomorphism. For the second branch of method, Fisherman studied the constraint generation where explicit score matching training loss using the log barrier method and the reflected Brownian motion. However, the existing methods still do not provide the optimal transport guarantees. To fill in that gap, we consider the reflected Schrödinger bridge problem, and we first studied the stochastic optimal control formulation. So basically, we try to minimize a control cost under the constraint of a continuity equation or a transport equation with some boundary assumptions. And we know solving a constraint optimization problem is hard, but we can resort to the Lagrangian formulation and apply a Lagrangian multiplier to give us an easier solvable training loss. And by using the integration by parts, we can have the following training loss. And if we further minimize the loss with respect to U, we can get the optimal U to be G times the gradient of the multiplier. We further apply the exponential transform to get the forward potential function, and further set this loss at 0. We can recover the backward chromograph equation with Newman conditions. Next, we define the backward potential function to be rho star of the forward potential function, where rho star is the optimal density of the forward diffusion given the optimal control. And we can now have the forward chromograph equation with Rubin condition. And this is also known as the Fokker-Planck equation with Rubin condition. So numerically, solving PDE in high-dimensional meshes is quite challenging, and it often causes the curse of dimensionality issue. To tackle that issue, we may resort to a set of reflected forward-backward SDEs, meaning we can consider a Schrödinger system with Newman boundary conditions and use the reflected forward-backward SDE to solve the PDE. So basically, the SDE is almost the same as the vanilla SDE, except that we need to include the local time to take care of the particles around the boundaries. And of course, the optimal control are not known so far. We need to use tools such as nonlinear Feynman-Cut formula to give us some reasonable approximation. So we can apply the generalized Ito formula to this YT, and we can get a training loss, which is based on some integral of a zeta function. Here, zeta includes a blue term, which is actually the key part to make sure the transport is optimal. And if we remove this blue term over here, the training loss will be recovered to the standard implicit score matching training loss. And also we include a local time over here and to take care of the particles. And for a deeper understanding of Schrödinger bridge, we can connect the Schrödinger bridge with optimal transport. So basically, the dynamic Schrödinger bridge on bounded domain omega proposed to solve the optimal coupling in the class of path measures, where the beginning of the measure is mu star, the ending of the measure is nu star. Q till is a prior measure, and it's often caused by, for example, the reflected Brownian motion or the reflected oil process. And we can further project the path space into the product space, meaning if we apply the disintegration of measures, we can decompose the dynamic Schrödinger bridge as a static Schrödinger bridge and a different bridge. If we assume some good estimation of the different bridge, the static Schrödinger bridge is actually seamlessly connected to the entropic optimal transport. So meaning we can leverage the efficient computational tools to help us solve the Schrödinger bridge problem. We know the static Schrödinger bridge is a constraint optimization problem which may not be feasible in computation. However, the constraint optimization possesses a fairly friendly dual formulation. Given mild assumptions, the minimization of the KL divergence of the static primal will be equivalent to solving the maximum of the dual function, and there is no duality gap. So this means that we can solve the Schrödinger bridge using the alternative maximization. So basically, we can fix one potential and try to maximize another potential, and we keep this process until we reach some equilibrium. And from a geometric perspective, this alternating maximization corresponds to the alternating projections, meaning the maximization of the potential function is equivalent to mapping the marginal to the mapping the coupling to the desired marginals. So given ideal projections and with some coupling initialized somewhere, we can actually map the coupling to the desired coupling where the first marginal is mu star, and then we can map the coupling into the second set of coupling where the second marginal is nu star. We can repeat this process until we reach some equilibrium where the pi star is the projection onto the Gibbs kernel. And of course, in practice, solving exact projection is quite expensive. We can resort to the approximate projections. And given these approximate projections, we know achieving this exact pi star may not be so easy, and but our solution may somehow be close to the exact solutions. And in the next several slides, we're gonna identify the convergence analysis to see how far away our solution is. So recall that the dynamic and Schrödinger, the dynamic and static Schrödinger bridge both yield nice structural properties, meaning we can represent the dynamic coupling and static coupling in terms of potential functions associated with the kernels. And here, the summation of the potential functions is unique, and the analysis hinges on the study of the squared term of the sum of the potential. And to facilitate the analysis and avoid inducing the inner product term, it's quite standard to build centered potentials as follows. So basically, we can avoid the unexpected inner product and lead to the equation of the squared sum will equivalent to the sum of the squared. This is conducted by a centered algorithm as follows. So basically, the first iterate of the potential function will be exactly the same as the standard Singh algorithm, but for the second iterate, we cannot do the standard Singh algorithm, but rather we need to include some normalizer to make sure the potential is properly centered. And of course, in our setting, since we're using approximate marginals, how to ensure the potential is centered in the approximate marginals is kind of crucial in our setup. And we did our change as follows. And we also lay out some standard assumptions like the Lipschitz assumption and the linear growth assumption for the drift and the diffusion term to make sure the tail of the distribution decreases sufficiently fast. And such assumption also ensures the second moment to be bounded. The second assumption would be on the domain. We assume the domain is bounded and has a smooth boundary. So in that case, we can have a proper normal vector for each particle around the boundary, and we can compute the reflection. The third assumption is about the smooth measure. We want the energy function to be differentiable. And then the fourth assumption is about the approximation. We want to have some sort of approximation. And here the approximation is weaker than the uniform approximation. And we notice here that our approximation can be pretty bad in the tails because this is reasonable. And for example, in the tail of the distribution, we often don't have so many samples. In that case, it's quite reasonable to assume a bad estimation around the tails. And this assumption is also very popular. We don't need to worry about the second term in the X because in the first assumption, we have ensured the second moment to be bounded. So this X term will be taken good care of later. So now we can have the first auxiliary result about the convergence of the dual and the potential functions. By exploiting the strong convexity of the potential function with respect to the concave dual, we can get the convergence of the dual and the convergence of the potential functions. So basically, it includes a linear convergence thanks to the convergence of the optimal transport in constrained settings. And also, since there is a contraction, a geometric contraction, because the transport cost is exactly larger than 0. This means that the perturbation over here would be independent of the number of iterations. At least we can guarantee that given sufficient many of iterations, the perturbation won't be too far away from the ground truth. And also we notice that the symmetry operation does not change the structural property, but the uniqueness of the summation of the potential functions. Now we can get our desired convergence of the static couplings. We quantified this result using W1 distance, and we found the W1 distance between pi k, which is the empirical coupling, and the optimal coupling pi star is upper bounded by a linear convergence term together with perturbation over here. So this is not the first result. Actually, Gandas also identified an elegant result using a geometrical approach. However, their approach is based on the advanced geometric tools based on the Hilbert-Birkhoff metric, while our result does not require advanced tools and may be more friendly to the readers. And from this result, we can also show that to obtain some W star W1 distance, we can run an order of log of 1/epsilon iterations to achieve this goal. We acknowledge that the constant over here seems to be kind of intimidating, but don't worry, because since C/epsilon equals to C/epsilon, this means we can apply a large regularizer or a large temperature in the forward diffusion to accelerate the convergence. Of course, there will be some like a bias and variance trade-off involved, but we can tune this performance based on some like cross-validation or something. So the end of the result is not a formal result, but some kind of like a conjecture. Actually, the convergence of the dynamic coupling is still an open problem, but it's an important problem. It's an important problem and also a quite interesting result. So recall that we have a bridge representation for the couplings, and we can represent the dynamic coupling as a static coupling with some diffusion bridge. So by the triangle inequality of the W1 distance, we can upper bound the W1 distance of the dynamic couplings by the static coupling convergence and the convergence of the diffusion bridge. So this means that in the future, if we can identify the convergence of the diffusion bridge, we can figure out the convergence of the dynamic coupling. So it will include the linear convergence based on the single horn algorithm. It includes a perturbation, but thanks to the contraction in the optimal transport in constraint domains, the perturbation is independent of the number of iterations. So this is the end of the theoretical analysis. Let's switch gear to talk about the empirical side. So we first try to generate the spatial shape and the domain of a heart. And we also try to generate the Gaussian mixtures and the domain of octagon. And we can see the generation quality seems to be nice. We also checked the vector field and found that the transport seems to be somehow efficient and slightly optimized. We also try to generate image data in cube domains. And unlike the previous hard domain or some other domains, the cube domain is fairly easy to implement. So basically, we only need to include 2 lines of code over here to incur the reflections to make sure the samples are all like guided towards the desired cube domain. And we can then do the standard image generation. And we can see the generation quality for CFAR and the ImageNet seems to be nice. And we also checked the numerics in terms of FID, and we found this reflection operation will slightly improve the Schrödinger bridge problem from 3.01 to some marginally better performance. However, in the code implementation, we only need to include 2 lines of code, and this makes the method in a much more principled formulation, and even for the improve the performance. So in the last example, we try to generate data of simplex that satisfy the simplex constraint. We include the stick breaking method as a benchmark, and we found the stick breaking method already works fairly well. But our method still improves the highly optimized baseline. So this shows the superiority of our approach in constraint generation. So to summarize, we introduced the reflected Schrödinger bridge to study unconstrained generation with optimal transport properties. And we established connections between dynamic Schrödinger bridge, static Schrödinger bridge, in terms of both of primal and dual formulations. We proved the convergence of the static couplings and paved the way for studying the convergence of general dynamic couplings. So the good news is, since we have a standard linear convergence of optimal transport, and studying the reflected Schrödinger bridge on a bounded domain will nicely inherit the linear convergence of optimal transport. And this will make sure the perturbation of our result will be independent of the number of iterations. And there is some ongoing work, like they try to propose some exponential convergence of the optimal transport without a human bounded domains. And we look forward to the progress in that area. And in the end, we demonstrated the efficacy of the reflected Schrödinger bridge in constrained synthetic data generation, image generation, and the simplex data generation. Yeah. So this is the end of the presentation, and thank you for your time and attention. Yeah.
Thank you, Wei. So we have time for questions. Let's start from the audience here. So I have one quick clarification question as the audience thinks. And also, can we have the next speaker come up, the third talk speaker? Yeah. So could you explain, I'm not very familiar with the existing work here, but could you explain in the image generation experiment, what are the constraints that you use?
The constraint is the cube domain, meaning, for example, the pixels are often like constrained to be within a domain of 0, 1, or from 0 to 156. And whenever a particle is near the boundary, we need to ensure the pixel values is within the domain. So the empirical method implemented this idea using the ad hoc thresholding. So this is nice, and empirically it works okay, but it's still not in the right implementation. So in our setup, we can implement this idea using the reflection operations. For example, if we assume the domain is 0, 1, and if we have a particle at like 0.99, and recall that Brownian motion is in the full space. When we have some noise, it can easily get some value of like 1.02, right? And that's physically meaningless. But thanks to the reflection operation, the 1.02 can be reflected to 0.98. So this is how the 2 lines of code can work over here. Just include some like reflection. It's like 2 minus x if x goes beyond the boundary.
Okay, I understand. Thank you. Thank you for the clarification. Any other questions from the? Okay, then we'll move on to the next speaker. Thank you, Ray. We'll do some switching here. Next, we have Antonia. She's going to present her paper, Picks to Code, Learning to Compose Neural Visual Concepts as Programs.
So, hi everyone, I'm Antonia Wüst from the AI and Machine Learning Lab at TU Darmstadt in Germany. And today I'd like to present our work, Picks to Code, Learning to Compose Neural Visual Concepts as Programs. And yeah, perfect. And this work is together with my colleagues Wolfgang Stammer, Quentin Delfosse, Devendra Dhami, and Kristian Kersting. And our work is motivated by abstract visual concepts. And if you think about it, those concepts are very present in everyday lives. For example, in a driving situation, you have to observe your surrounding and take into account various objects and reason based on that whether you, for example, are allowed to continue driving or you need to stop. Also, for example, if you want to grab some food at a food truck, you have to see whether there is a queue of people, how long it is, where is the end of that line. So we have to observe that concept of a queue. And to us humans, this is quite natural, but if we want AI systems to understand our world and act in our world, they need to understand those concepts as well. And they still struggle quite a bit. So for our work, we looked at a scenario where we want to learn unsupervised concepts. And for that, we assume that we have positive and negative image examples of concepts. And our goal is to learn a concept that describes how to separate those images. And you can do that to some extent already with neural models, but these are, as you know, not so well interpretable, and also they have some trouble with generalization. And for that reason, we want to learn the concept in a way that it is inspectable for humans, also revisable if there is some suboptimal behavior. And importantly, also, if we have new data of this concept, which might be a bit more complex, like here we have more objects in the scene, we still want that our concept is able to classify this image correctly. And a field that is already quite good at generalization and learning based on few examples is program synthesis. And here there were already quite a lot of methods developed, but applied to domains like list processing or text editing. And here you can see that those methods already perform quite well in those domains. One example, if you're not familiar with program synthesis, is given here. Usually you have a task which is in that form that you have an input and an output, and your goal is to find a program that can map from this input to the output. And here the underlying program that is searched for is the sum of this input list. So the input is supposed to be, the elements in the list are supposed to be summed up to form the output. And a cool thing about programs is that they are themselves already quite general. So if we are processing lists, it doesn't matter if we have 3 elements in the list or 100 elements, the program will still perform the same way, like iterate over every element. And this becomes important later. Also, programs are interpretable, and we can revise them, like edit the program. So this motivates our work. We want to learn visual concepts via program synthesis. So we want to find programs that are able to determine the visual concepts that are present in images. So for example, for one visual concept, here all objects are spheres. We want to formulate tasks. The input is the image and the output is whether the image belongs to the concept or not. And with our system picks the code, we want to get a program that can exactly do this mapping from the image to the output. And the cool thing here is then that the program is able to classify images, but also it is interpretable. So it itself is kind of encoding the concept. And how do we do that? As I said before, program synthesis has been applied mostly to symbolic domains like text editing or list processing. And so we decided to first map the image to some symbolic representation. And this is done by an object extractor that is processing each image and detecting the objects in the image so that we get a bounding box and also various attributes of the objects. So for this example image here, we get 2 symbolic representations for the 2 objects with the bounding box and the attributes like size, shape, and so on. And these representations are then in the form of a list. So one image is encoded as a list of objects, and they are then associated with the respective concept label. And this result is then our program synthesis task with which we can perform the search for programs. And the method we are using here is a method based on dreamcoder, which is a method based on a wake-sleep algorithm where we have a library and a code model that bootstrap each other. And the code model is a neural model that can predict program paths based on the given task. So it's kind of a posterior based on the task that produces program primitives. Those primitives are predefined in a library, and they are very basic elements like equal, for all, map, and so on. So basic parts from which we can build our programs. And then during training, this model is trained to produce the most likely primitives for a given task. And for program synthesis, we perform an enumerative search, which is guided by the model. So we sample from the model and get the most likely primitives, build our programs based on that, and keep track which programs are the most likely. So that at the end of the search, we obtain a program that solves a task. And yeah, in the training process, as I said, the code model and the library bootstrap each other. So with the programs that are found here, we can update the library, which gives also a prior over the program primitives. And with the library, we can sample programs and input-output tasks to train the code model. And yeah. Also, a cool aspect of the library is that it can grow over time during the training. because during training, we obtain programs that solve for tasks. And if we see that there are some similarities in the programs, like here, this program checks for if all objects are spheres, and this one checks if all objects are cubes, and they are pretty similar. So this program can be abstracted, and the shape can just be a variable in this function. And this makes it easy to reuse concept parts for new concepts. And also a cool aspect of the library is that it's symbolic, so it's interpretable to humans, and you can even add some function parts or remove some function parts if that helps for your problems. Here again, overview of the method. We have input sets of visual concepts where we have positive and negative examples. We map them to a symbolic representation and formulate tasks. And then we perform program synthesis and obtain a program that can separate those images. And also this program can then be interpreted to natural language. For the evaluation, we looked at two evaluation data sets. One is the Kandinsky patterns, and the other one is the Curie benchmark. Kandinsky patterns are a bit more easy visual inputs, and the Curie benchmark is based on clever images. So this is a bit more challenging, and that's why we focus mostly on this data set for the evaluation. But basically both have some abstract concepts that are also compositional, so we have to check for multiple things. Yes. And for the evaluation, we compared to the baseline of the Curie benchmark, which is a neural model based on prototype networks. And to compare, we reported the class balance accuracy on test concepts. So you train on training concepts, and then you evaluate if you can solve new test concepts. And at first, we looked at just simple train test generalization. And one important thing about program synthesis is that it might happen that you are not able to solve every task because you have an enumerated search with a specified time, search timeout. So it can happen that you're not able to find a program that can solve your concept, but in most cases it did. And for these cases, we report the accuracy of those programs here, and you can see that this is quite high. But since we're comparing to a neural baseline, which is always able to produce an output and classify concepts, we assumed then just 50% accuracy for programs or like for concepts where we didn't find a program. And this is the accuracy that you can see here. So we thought this comparison would be a bit more fair. But still you can see that we outperform the baseline. Yeah, and this is the train test generalization, but the Curie benchmark has also different concept splits, which we call domain generalization concept splits, where you divide the train and test concepts based on some rules. So for example, in one of the split in the train concepts, there was never the color yellow important, but then in the test concepts checked for color yellow. For example, all objects are yellow, so you have to generalize and realize that the color yellow is suddenly important. Another generalization that we thought is very important is the generalization on the concept level itself. So if you have a concept, for example, all objects are cubes, then you want that this concept is still valid, even if there are more objects in the scene. And because, yeah, the concept itself doesn't change despite how many objects are in the scene. And so we decided to increase the samples of the Curie dataset for two concepts, and investigated how well the baseline performs and how well our programs perform on it. And this you can see here. So usually we had 5 objects in the scene, and then we created images with 8 and 10 concepts. And as you can see very well here, the baseline performance drops the more objects you have in the scene. But our program that we retrieved with Pix the Code still has a perfect accuracy, because we, in this case, found the program that perfectly encodes the concept. So it will always classify samples correctly. And then we considered another concept, which is all objects are metal and one is gray. So a bit more complex. And here also the baseline performance drops. And for Pixel Code, the program, we have 3 seeds here. And for 1 seed, we didn't find the perfect program. And that's why the accuracy is a bit lower here. But for 2 seeds, it was still the right concept. And as you can see, the accuracy is still way over the baseline. Now looking at the interpretability, because as I said, we want that the concepts are interpretable to us. And the way the programs are generated is in lambda calculus, which is a functional programming language. And it might not be directly readable for everyone. But what you can do is you can just take those programs and give them to an LLM and ask it to translate it for you. So if you're not so familiar with lambda calculus, you can also ask for natural language translation directly. But one thing that is cool about the lambda programs is that you can see here already that there are a lot of parts that are reused for different concepts. For example, we have the concept all objects are cubes, which is encoded by this program. And here down there, you have the concept all objects are brown or all objects are cubes. And as you can see here, there's this program part that is also up here for that concept. So that you can really see the compositionality of our programs. And then, as I mentioned, we also want to be able to revise our model. And because the model has a neurosymbolic architecture, we can also revise the model on an architecture level, or like in this example here, we can directly interact with the library. You might have noticed before that the counting split of Curie, there our model didn't perform as well. So we are a bit below the baseline. And we think this is probably due to the less examples of counting in the training concepts. And so we thought, okay, what is when we just add some counting primitives to the library? And so to help the model a bit to understand, okay, counting is something that is important. And once we did that and we trained for 1 iteration, we improved our performance a lot and over 80%, gained over 80% accuracy on the test concepts. So you can improve the performance by adding elements to the library, but sometimes it might happen that you learn something that is not optimal, that is maybe confounding your training. And therefore we created an illustrative showcase where we have the concept all objects are metal and there exists a cube. But in the training examples of this concept, we implemented a confounder. So all objects of that concept are also having a color cyan. So this color is kind of a shortcut with which you can learn the concept. And this is exactly what happened here in this case, where we have examples of the concept. So the objects are metal and there's existing a cube, but also the objects are all cyan. So the program is then just focusing on this color and of course able to predict the right label for the training images. But if you evaluate then the program on other examples of the concept, like here where we don't have the color sign, but it's still valid examples of the concept, then the program will classify them incorrectly. And for this scenario, what you can do is you can just, if you identify this confounder, remove the color sign from the library. So the primitives that are responsible for looking for checking that objects have the color sign, and then also retrain the model. And by that, you can overcome this confounding. So your model is not looking, or the program is not looking for the color sign anymore. And this is also a cool aspect because you don't have to change your data, you just have to edit the library here. Then these experiments were all on clever data, which is of course synthetic. but we think it would be also cool to extend our method to real-world images. And for that, we looked into the MS COCO data set and created some concepts ourselves just to try a bit if it would be feasible to do that. And for example, one concept was it exists a person and it exists a dog, and then we selected the images of the data set based on that and checked whether pixel code can learn programs that can classify this concept correctly. And there we obtained around 90% accuracy on some of the concepts. Counting persons was still a bit harder, but we are optimistic that it could be a cool direction to go into in future work. Yeah, so with that, I would like to conclude. In our work, we presented the method Pix2Code, which is a method based on program synthesis to learn visual concepts that are interpretable and revisable and also have high generalization abilities. And yeah, if you want to learn more, we have also our poster session tomorrow, or can check out the paper and of course also talk to us. Some of my colleagues are also here at the conference, and yeah, thank you.
Very nice talk, thank you. I will ask the first question, if that's okay. So the confounding case was very interesting. The one thing I observed here is that you are violating positivity. You are basically saying all of them are cyan color, right? So, but that's a very strong confounder. You could alternatively have a weaker confounder where you would not violate positivity. You would have some, but most of them would be cyan, but also other colors maybe. How would that perform in that case? And then would your fix still work in that case? Those are my two questions.
In the case when not every positive example has the color cyan, then it wouldn't focus on that, because right now it needs to, like every example needs to be classified correctly by the program. So then it would ignore that, that confounder. And regarding your second question, I think
So I'm saying if in that case, color would not be a way to fix that problem, I would think, right? So did you think about how would you fix that kind of weak confounder where the concept is not that clear cut? It's not just cyan, but you know, there's still confounding.
if there's a more complex confounder.
Yeah.
Yeah, okay. Then it might be more more complicated, because then you have to either, yeah, if you really know the complicated confounder, you could still try to remove elements from the library, but maybe it might then be easier to update some of the training examples to make sure that yeah, the confounding is mitigated. Yeah.
Thank you. Other questions from the audience?
Hi, thanks. Thanks for the nice presentation. And my question is partially related. So your methods depends on the symbolic dictionary that you give to build these programs, if I understand correctly.
Yeah.
So you showed us this confounding example in which you remove something from the library to remove a confounder. But what about the other way around? So you may find programs and therefore explanations that tell you something about what the model is doing, but you may not have added enough to your symbolic library to actually capture what the model is doing. So you may, if enough confounding is at play, you may walk away thinking the model is doing something that is maybe not entirely what the model is doing. Does that make sense? And have you thought about how to control for this?
So you mean the stuff with which you could describe the confounder is not present in the library? But then you would also not be able to build a program that is looking for the confounder, because you don't have the base primitives to build it.
So you may have given other primitives, and so you build programs based on those primitives, but the model is using other concepts and other notions to solve the task. So you will build programs that perhaps are very close to what the model is doing, but not fully capturing what the model is doing, because you haven't given enough
symbolic concepts.
Mhm. I mean, I think you would see either you would not get a program because what you have in the library is not sufficient to build a program that can classify the images correctly, or you would get a program, but then you would see it in the performance on test examples, I would say. So I think you either by looking at the program, make sense of it that it's probably not doing something correctly because of your domain knowledge or something, or you would need to have good testing examples to see if it really is able also to classify the test examples correctly, I would say. Or then if you realize that something is missing in your library, of course, you can then add it to check if the the program is then using these elements or not.
Thanks.
I think we have one more question here, and then we can. Right here. Here. Oh, there's one. Okay.
Yeah, so thanks for the presentation. I'm also interested in the confounding. So if I got this right, you assume to basically observe the confounder. Have you also looked into another interesting case where you don't observe the confounder, so it's latent, how you can detect it in that setting?
We haven't looked into that. I think here to have a relevant confounder, you also have to have it somehow in your training examples, because if it's not present in the training examples.
Well, it's still present in the training examples. I'm just saying that you don't observe it.
But then you should somehow be able to see it in the program that it's focusing on something that doesn't make sense, or.
But for this, you need a human expert, right?
Yeah, of course, yeah.
But if you don't have a human looking at or finding out what these confounders are, how would you do it then?
Yeah.
I mean, you would need some causal engine there, right? That we are not having in this. That would be the answer.
Yeah.
Take the confounder and do something with it. It's related to my question, actually.
Okay.
Yeah. Let's say last question, and then
Thank you for the nice talk. My question is also related to your example of confounder, but from another aspect. How do you find your most fitting or most probable program? For example, if all objects are spheres and all objects are purple, like all objects are purple spheres is a shorter one. So from a Bayesian point of view, it would be more likely. Or do you incorporate some knowledge of that must exist a rule? How do you do that?
There is a bias to shorter programs. So if there is the possibility to obtain a shorter program, then this is the one that is picked. And for the color versus shape, you have the prior of the library. So if in your training examples, the color purple is more present than the shape cube, then probably it would select the purple. But yeah, it's based on the training data then a bit to what it would be more.
All right, let's thank Antonia again. Do we have Nicolò?
This is not my slide, but
Next, we have Nicolò, who's going to talk about his paper, Normalizing flows for conformal regression.
Nicole, thank you. Okay, this talk is about conformal prediction. Yesterday we had a nice introduction, and I'm talking about making conformal prediction more less efficient and how to link conditional and marginal validity. Yes. RHUL here is means Royal Holloway, and this is actually the birthplace of conformal prediction, because Volodya Vogt, the inventor of conformal prediction, is like my office neighbor. And 2 doors away, there is Alex Gamberman, the second author of the book. It was in the plot at the yesterday tutorial, the citation plots exploded. Okay, so they don't appear here in the author list, but I'm sure that they contribute in some like hidden way to this work. And yeah, this was the plan, but actually we had yesterday a nice introduction. So the first 2 chapters were a bit of an overview of conformal prediction, conformal and marginal and conditional validity. I will go a bit faster, but please stop me if something is unclear. And my contribution is actually the 3rd chapter here about what I call calibration training. This is the new bit. And the last slides are like a toy example that I implemented on just for this talk. There is a Python notebook. If you're interested, I will be happy to share. So we can start. I focus on regression, and we have some data, labeled data, just to remind that this is all about supervised learning. And I assume IID because it's simple. Probably this is not the, we can relax a little bit this assumption, but let's keep it simple here. And we also have a pre-trained point predictor. Point predictor is just a prediction model, but the key point here is that it's pre-trained. That means that we don't need to know the structure of this model, or we don't need to have access to the data that have been used for training it, or how the model was trained. This, I think, is an advantage compared to like conformal quantized regression, conformalized quantized regression, where you need to train a big model to get a good performance. For example, this approach would apply also to a big language model trained by Google on millions of Wikipedia pages, because we don't touch the model. And we just need to some data from the task we need to solve. And this is as usual in a conformal prediction. We make no assumption on I mean the quality of the prediction of F or the data distribution, data generating distribution. And okay, for this work, we split, we have a data set, but we split in 3. Usually we have just calibration and test. And here we have a training data. I just told you that we don't need to train, but here the training is on the conformal prediction base. So we are given the prediction model, and we train what is called the conformal prediction algorithm. Normally, this is not needed, because normally standard conformal prediction algorithms are not trained. It's just something that you put on top of any prediction algorithm to get confidence prediction interval, so some uncertainty estimation. And so this is not required in the standard setup. But training can make the conformal prediction more flexible, task-specific, and also in this case, I will show how training can improve adaptivity. Adaptivity means here local adaptivity to an input towards input conditional validity, if you remind yesterday tutorial. So Next 3 slides, just a review of how you compute the prediction interval. As usual, this is a CP or conformal prediction is an uncertainty estimation tool. So it will promote a point prediction to a set. The set is living in the label space, and the set has a property that the true label is contained in the set with lower bounded probability. The key point here is that the probability is taken over the test object. Of course, we see Y test, there is also X test somewhere, but also over the entire calibration set. So part of the ILD data that I introduced before, and the dependence on that data point is hidden in CA. So the CA here is the prediction set. How? Let's see how we compute the prediction set. Okay, this is the minimal assumption we need. If the data are IID, this is satisfied, so they are also exchangeable. I don't prove it because that was proven also in during the tutorial. And what we need, we pick a conformity function. As here we focus on regression, we use this. It is the most popular conformity function, and I think 90% of work on conformal regression use this conformity function. There is not huge creativity in the conformal prediction literature about conformity function. In some sense, this is also because we want to produce some intervals in the label space, so it makes sense. Okay, but let's pick this conformity function, and we compute the scores for all the data in the calibration set. And then what we need to do is to compute the smallest element of this, the NA small element of this conformity scores. And the prediction set will have this 4. And I skipped the proof. This is less general than what you saw yesterday because it's for IID. And more intuitively, what are we doing? The N alpha smallest element is just approximating from above the quantile, the 1 minus alpha quantile of the score distribution. What distribution? It depends on which kind of validity bound you want to achieve. And as here, we compute the scores of all samples. In this case, what we get is marginal validity. So again, the probability here is over the entire calibration set and the test. So in this case, the quantile is the quantile of the marginal distribution. Okay, and since we use all sample to compute this quantile, we get only, this is a number. Because regression, one-dimensional regression, this is just a value. This is a value of the score. And so we have one value for the entire input space. This means all the prediction interval will have the same size. No matter what X test is here, QA is the width of the prediction interval, and will be the same for all. Okay, so do we need something more? Probably yes, because in practice, the model has not the same performance everywhere, not the same uncertainty everywhere. Even if you try MNIST data to train a classifier and distinguish between 0 and 1, it's easier than distinguishing 0 from 8, for example. So what we would like to achieve is the prediction interval is like varying in shape, and it's larger where f is uncertain and smaller where f is more confident. Translation, the fixed side prediction intervals are inefficient. The concept of inefficiency is a bit fuzzy. Let's say, keep in mind that can be just the average size of the prediction intervals. And but what happens if instead we focus on a single point, on a single region of the input space? Well, with the construction that how we built this CA means that this validity bound doesn't hold. Why? Because if we focus on a specific point in the input space, that means that we are conditioning on that value of the input. And so Y test, and so the score will be generated by the conditional distribution, while the CA here computed from the quantile of the marginal distribution. So in some sense, we have the quantile of a distribution, and we are evaluating something coming from another distribution. So this doesn't hold, and I point this out just because I like to see this as a non-exchangeability problem. And it's not that surprising because exchangeability is the only assumption for conformal prediction, and if something doesn't work, it means that this assumption is violated. And okay, this probably is a bit intuitive, but you can see why this conditional validity doesn't hold. And okay, can we just quick fix this? Because if we can replace the wrong quantile with the right quantile, so the quantile of the conditional distribution, in principle, we could achieve the conditional validity. But of course, computing the conditional quantile is impossible because we would need an infinite amount of data, and especially a set of calibration samples for each different X tests. There was a proof about of this no-go theorem. Yes, there was a sketch of the proof. So this is considered impossible. Okay, so this is a bit depressing, but so let's take a step back and think about what happens if the conditional probability is equal to the marginal probability. Okay, in this case, conditional validity and marginal validity will be the same, and everything holds automatically. Is this possible in practice? No. And for a general task, this is not true. But there are cases where we can make this happen. And how do we do? For example, okay, this is a very a toy model where the output is generated in this specific way. We have access to the exact model. But what can we do is to redefine the conformity score in a way that all the dependence on the input of the distribution is cancelled out. And so we obtain that the distribution of B doesn't depend explicitly on X. And so this equality holds. Okay, this is just really a simple example, but this is just to illustrate the idea. Can we generalize this? And what can we do if we don't know the true model? Okay, let's learn this transformation of conformity score from the data. And this is what I propose to do here. So we start from a general transformation, and we train this transformation from the data. As the transformation is acting on random variables and we need this to be invertible, this is actually the definition of a normalizing flow that is transforming a distribution into another by defining a deterministic transformation of the random variable. And normalizing flow has been used in many inference tasks, and there are a very different ways to train them. And you can transform a source distribution into a target distribution. And in our case, the target distribution, the source distribution is the distribution of the conformity score, and the target is this factorized distribution where you see here the this conditional equal to marginal probability requirements holds. So this is the idea I been implementing. In the next, I will go through this example or toy model. I'm repeating what I said up to here with some examples. So if you have any questions, please ask. Or we can just postpone this. Okay, so we have, in this case, I generated some IID data. You see that the point here is that the output is very noisy. Sorry, psi is big here. It's very noisy for x bigger than 0.5 and is almost clean for x smaller than 0.5. And we also have a pre-trained model. Okay, in this case, the polynomial just to fix it. And this is what people normally call heteroscedastic data. You see that here everything is fine, and here the uncertainty is much bigger. If we train the model, and the model is pretty good everywhere, but of course here the uncertainty is much bigger than here. So we expect conformal standard conformal prediction to be not that efficient in this case. As I told you, we split in 3 data sets, and train is used for training the conformity score and calibration and test. Okay, calibration to complete the quantite actually, and test is to measure the performance of the model. And this is a summary of the algorithm that you can implement. It's really 3 lines. We pick the usual conformity score. We compute the calibration scores. We rank them. We pick the smallest, the n alpha smallest element. Here you have the expression if you want. And this is an approximation of the 1 minus alpha quantile. And then the prediction interval as this form. QA is a number, so this is fixed. And this is what we get. So this is not fixed. This is depends on this is the underlying model is like going there, but the width of the prediction band or the uncertainty band is the same. And you see that to be valid, the algorithm is forced to be really inefficient here, because you see that the cover, the build category that is guaranteed by construction is 0.9. So if you count, I think there are 100 points. There should be not more than 10 points outside the bands. You can just confirm. So it's valid, but the size, the constant size is not a good strategy. Okay, so yeah, here I implemented the like in the toy model, the example, the motivated example. You can do the same. And you fit a pre-trained model, you fit a model of the residual, and you reweight, and you see that when you invert the transformation, you get something that is more adaptive over the input space. And how this works, this is working because where the model is uncertain, you make the sorry, when the model is reliable, you pay a bigger price when you make errors. And in some sense, this is adjusting the difference between the distribution before 0.5 and after 0.5. And then, okay, we implement the proposed method where the form is more or less the same, forget about the log, and we train it by imposing this factorization. Why the log? Because we have, this is a normalizing flow, and the target distribution is this factorized. We train by maximum likelihood, and we want to pick as a arbitrary target the Gaussian. So this is why they will put the log to ensure that the image of the transformation is the correct one. And the objective function is very simple. See here the Gaussian, and this is actually a constant, so can be skipped. And this is appears here because we are evaluating the at the transformed slope. And this is, yeah, thank you. This is just to show this is the algorithm, and this is the performance of the model. And if we compare the conditional distribution, these are the quantized, the conditional quantized, you see that the proposed model is much better than the others. This is the original score, and this is the reweighting, and this is the normalizing flow approach. Okay, if you want more details, all these pictures are also here in the poster. I will show you tomorrow, I guess, and you can come to my poster and we discuss. And there is also something about validity bounds. Thank you. Sorry for the delay.
Thank you. Any questions from the audience? Nicolò.
Yeah, so thanks for the talk. If you fit a structural equation model with independent noise for a causal, just for a causal goal, then this is basically the same because your noise is independent. So then it's then you have this transformation for free, right? Yeah. Yeah. Okay. Okay. Yeah.
You insert was just, and we insert this line, but then everything goes as usual in conformal prediction. So yes, of course, if you have a better strategy to even to figure out how this this transformation should be, this is a great advantage because choosing the model class here is tricky. Because it should be an invertible transformation. I guess the structural equation were all further invertibility. Yeah. So, but this is just this line that you insert here, and then you go as usual. Yeah. So if you replace this definition with another, then everything should work. Yeah. Thank you.
All right, let's thank Nicolò. Our next speaker is Elliot, and he's going to talk about the pathologies of deep heteroscedastic regression.
All right. Hello, thank you. Yeah, I'll be presenting Understanding Pathologies of Deep Heteroscedastic Regression. My name's Elliot. I'm a PhD student from the University of California, Irvine. This was joint work with collaborators Alex Boyd, Vincent Fortune, and my advisor, Stefan Mont. So I guess nicely building off the previous talk, heteroscedastic data. It's just data where we have noise that is varying across the input space. Here we have an example. This comes up in many real world data applications. You could think of some simple examples, could be plotting age versus height in the population or income against expenditure on meals. Now, if we want to model this data because we can see that there's differences in the amount of noise in it, we should be accounting for that. And what we can do is we can try to model a mean and we can try to model a variance separately. And then hopefully if they're both adaptive over the space, we can get a nice fit that could look something like this. So on the left, we're looking at a plot of the mean fit with standard deviations, 1 and 2 of them added and subtracted to it. We can see that the mean doesn't overfit and the standard deviations roughly adapt to the data. Even more explicitly on the right side, we can see how the standard deviation is fitted through the absolute residuals. It's reflecting the fanning nature of the data as it increases. And also note that here we've split the data into a train and test set in orange and green, and it looks like it's doing about as well on both of them. This is really nice. So this seems like the problem solved, but in practice, if we try to model these two functions with neural networks for a mean and neural network for a variance, we end up with fits that look a little more like this. Quite nasty overfitting, both in the mean and in the variance. We're not happy with this. And almost none of the green residuals are actually even captured by this uncertainty. Well, what if we add regularization? Well, if we don't do it quite right, we might over-regularize, wash everything out, and just learn marginal variances and marginal means, also useless. So what if we tinker a bit more? Okay, we have a good variance now, but we have a bad mean. Or we could do it again, and now we have a bad mean, and we have a good variance. So the issue effectively is we have two networks that are competing to explain the data. We can explain it with a good mean, we can explain it with a good variance, but we kind of want somewhere in between. So our contributions to this problem are, we note that it's quite hard to fit, and we identify a phase transition in heteroscedastic regression models. We develop an analytic field theory to try to qualitatively describe this transition between over and under fitting. And finally, based off of this, we provide a better informed hyperparameter search of the regularization space that is built on top of this analytic field theoretic description. So some notation in the model written out a bit more formally. Our data set, we assume that we have XY pairs. We have n of them. The x's can be multivariate. The y's we assume to be scalar. And we assume that the y's conditional on our x's are following some normal distribution according to a mean function mu, which is going to be adaptive to the data. And similarly, some standard deviation function sigma, which also varies across the input space. Now, as I mentioned before, we're going to try to do this with neural networks. We're going to denote this with hats, and also the mean is parameterized by parameters theta, and the variance with phi's. And also, I apologize, I'm sort of going to swap between standard deviations, variances, precisions. They all sort of mean the same thing. And this is not a new idea. This was a model that was sort of introduced in 1994 by Nixon Weigand, and then recent work, it seems like people have started looking at this type of modeling framework again, and they've also identified that this is kind of hard to fit. However, much of their work has focused a bit more on techniques to try to get these models to fit. Ours is trying to focus more on why is this occurring, why is it hard to fit? So the most natural way to try to fit these models would be to look at the MLE. Here we have something that probably looks very familiar. It's just your normal likelihood, and we're plugging in our neural networks. But there's a few problems with this. Namely, if we have really deep neural networks that are capable of overfitting, in this first term, that residual piece can effectively disappear. Now all that's left in our objective are the variances or the standard deviations to learn. We're going to be incentivized to push all of these standard deviations to 0. You could also think of this intuitively as if we fit every data point, there is no noise, the standard deviation is 0. However, this is going to lead to some computational issues. We're going to have negative infinity when we take logs of 0, And we're also very naively in the first term dividing 0 by 0, and these are just going to cause instabilities in the fitting. Now, if the issue is overfitting, again, maybe we can turn to regularization. So here we're introducing a parameterization with alpha being how much to put this L2 penalty onto the parameters of our mean network, and beta how much of a penalty to place onto the parameters of our variance network. As alpha goes to infinity or beta goes to infinity, we're going to be inducing flat functions. And if we send these back to 0, we just recover our MLE to begin with. It's fairly interpretable and quite intuitive, right? But there's a little bit of a problem. We have to figure out how to choose this alpha and this beta. We're going to have to look at some sort of regularization space that's two-dimensional. You could think of alpha maybe being regularizer 1 and beta being regularizer 2. And across this whole grid, we're going to have to look across this whole blue box, and not just this blue box, it really just extends to positive infinity on each of these axes. It's a really big space. Now, it would be really nice if we could just search this little box right here instead. And to do that, we do a reparameterization of our loss. Now we express this in terms of rhos and gammas. And rho and gamma can be interpreted as weightings. So rho, which is what we have on the MLE term, is going to determine how much of the importance is being placed onto the likelihood versus onto the regularizers. And in this notation, rho bar and gamma bar just denote 1 minus gamma and 1 minus rho. Now, what gamma's doing is it's determining how much of our penalty do we want to put onto our mean versus our variance. So as rho goes to 1, we're recovering our MLE again. As rho goes to 0, we're basically just trying to please our regularizers. As gamma goes to 1, we're just going to be penalizing our mean. And as gamma goes to 0, we're just going to be penalizing our variance. So it's a completely one-to-one transformation of that original alpha beta regularization scheme I presented before. But the advantage of this is the entire space is going to be searchable in a much more amenable way. So now a brief aside into phase diagrams for a slightly different context. Here we have a phase diagram of water. On one axis, we have the pressure and the other the temperature. For different combinations of pressure and temperature, we see water show up as solid, liquid, or gas. Now we can think of our problem in the same way as that grid you're looking at before with rho and gamma on the axes. For different types of combinations of regularizers, we expect to discover different models that exhibit different types of overfitting, different types of underfitting, and different types of hopefully well-calibrated fits. So that is to say, what was pressure and temperature is now rho and gamma, solid, liquid, gas, overfitting, underfitting, nicely calibrated. To try to understand this physical system, we're going to derive a field theory, and we're going to apply this to our heteroscedastic regression models. And this is what we empirically found to be the phase diagram for heteroscedastic regression models. We have gamma again on the left, on the y-axis, and then we have rho on the x-axis. And what we're seeing in the middle and the right plots are representative fits coming from these different regions. Again, the MLE type fits are going to be on the right side when rho is going to 1, and the very data ignoring underfitting ones are going to be on the left-hand side where we're not really looking at them. And then we see, again, we get these overfitting means. That's in this O1 region where the mean is very under-regularized. And on the flip side, we get overfitting in the variance as we shift upwards and we don't regularize the variance so much. Most notably, though, we found that there was this region S where we seem to be getting generalizable models. And this ideally is the models that we would like to be plucking out of this phase diagram. So how did we move from neural networks to field theory? This is our complete field theory. It's a bit of a mess if you just look at it, but it's really not so intimidating. It's the same likelihood as we had with the neural networks for the MLE plus the regularization. But instead of a sum over data points, we're now going to be integrating over the data density. And we're treating Y as a stochastic process. We no longer have parameters for our models. Note that this field theory is over the function mu hat and lambda hat, whereas before we were looking at that loss over the parameters theta and phi, right? So now we're looking directly at these functions and trying to learn them. So instead of penalizing parameters theta or phi, we apply penalties directly onto the functions themselves through the Dirichlet energy. That is just the derivative over the 2 norm of the gradients. And sorry. And then finally, we're going to realize that it's still a bit too complicated and just think of a single realization from the stochastic process and simplify it to a single integral. Now, working off of this, we can try to, in summary, we cast the data distribution xy over a stochastic process. We replace our penalties from the parameters, put them onto the functions themselves, and then we rewrite our loss as a functional over infinite dimensional functions instead of the parameters. Now, if we want to find what this mu and this lambda should be for our field theory that would optimize it, we can take functional derivatives. And these are our functional derivatives taken respect to the mean and lambda. And just to be perfectly clear here, you may have noticed in the way that the likelihood is written on those previous slides now, lambda is a precision. It made the math a little bit easier. And again, our gamma bar and our rho bar are 1 minus gamma or rho, and the nabla symbol is denoting the Laplace operator. Now, we have these functional derivatives. What we do is we set them to 0 and solve for our functions to find necessary conditions for our solutions that would be optimal. And here they are. And now that we have these, we can start to do some analysis on it. And we found that in some limiting cases, such as if you take rho to 1, you essentially recover the MLE. We found that there's no solutions to the field theory, which is consistent with the MLE being unstable and blowing up. There's also no solutions if we take rho going to 0, which is to say we don't look at our data at all. And maybe most interestingly, if there is no regularization on the mean, there has to be regularization on the precision in order for there to be any solutions. Now, these are nice analytic results, but if we want to actually see these fits and how did we get that phase diagram, we discretized our field theory and used gradient-based optimization to find solutions mu hat star and lambda hat star. So here are grids of fits from the neural networks, they were MLPs that we fit, as well as fits coming from the field theory. It's a little bit overwhelming, but I'll try to walk us through this. Note that, again, we have gamma on the y-axis, rho on the x-axis. These are actual fits coming out, these regularization space. In the lower right, where we had the overfitting behavior before, we see that in both of them. Both of them have overfitting means in the lower right. In the upper right, this is our other sort of overfitting area. We have overfitting in the variances. And most notably in the MLPs, notice that as you move sort of down from the upper left to the lower right, there's this jump from completely not fitting the data to all of a sudden we're completely fitting every data point perfectly. And we would like to posit that this could be why it's so hard to fit these models. If you're moving around in regularization space and you make these slight nudges, you might end up in these very different sorts of under or overfitting. So that was a bit visually overwhelming. So we also computed some summary statistics of the fits for our field theory and on the MLPs. First was the Dirichlet energy. This is that same quantity that we were penalizing in the field theory, but we also computed it for our neural networks. It captures how expressive a function is. So when a function is sort of shifting around more quickly and steeply, we're going to get higher values. And if we had a perfectly flat function, this would be 0. We compute this both for precision and for the mean. And then there's 2 more metrics that we compute. We compute MSEs between the mean and the target. This assesses sort of how well our mean network is doing. And then we also computed the MSE between the standard deviation and the absolute residual as a way of measuring how well our standard deviation network was performing. So here are these quantities shown in phase diagrams. Across the rows, we have the different quantities, and across the columns, we have different data sets or data sets fit in different ways. So theoretical is the field theory. Sign is actually data from the same data generating process as the field theory, but fit with a neural network. And then the 4 remaining columns are data sets from the UCI machine learning repository. Notably, the sign data set is one-dimensional in terms of X, but the other data sets are multi-dimensional X's. So I think it's quite interesting and that these shapes are preserved across the data sets and across the dimension of X. And also that there's such strong agreement between them. And this is how we put together this sketch again. So looking back at this, before I mentioned that we'd like to end up in S, and I sort of hinted at one way that we could do that. And the issue is that for slightly different data sets, though the shapes were preserved, exactly where these transitions were or where we got the different over-under fitting or well calibrated fits, it shifted slightly, sort of unsurprisingly. But given that these shapes were so consistent, we thought that if we just moved from the upper left down to the lower right, we're guaranteed to cross through this S zone at some point. We're not going to claim optimality, but at least we know that we're going to get some fit that's going to look reasonable if we search along this line. So that's what we did here, is we searched along the row equals 1 minus gamma diagonal, upper left to lower right. And we're showing these results here for those same 4 quantities in this grid of 6 plots for those same data sets and models. The left-hand side of the line is the upper left-hand corner. The right part of the line is lower right. Now I want to draw your attention to these 2 MSE quantities. We placed stars on the points in regularization space across that diagonal that minimized the MSEs on the test data. What we found was that these stars are quite close to each other. Note here or there, and then there, and there. And in some cases, it actually corresponds to the exact same place. So we are saying this is where our S region is. So in summary, heteroscedastic regression models are difficult to fit. We developed a field theory to try to explain this phenomena. And our field theory suggests that these difficulties could arise from a phase transition in this regularization space. And finally, to try to exploit what we learned, we would suggest in this gamma row regularization, search from upper left down to lower right. Thank you very much, and please come by the poster. It'll be number 570 tomorrow.
Any questions from the audience? Yes.
Thank you. Yeah. Yeah, really cool talk. I was wondering on the interpretation is, so gamma's the regularization for the variance, right?
It's sort of how you attribute the regularization across the 2 models. So when it's 1, it's 100% of it being placed onto the mean. When it's 0, 100% of it's being placed on the variance. And if it's 0.5, it's equally attributed across the 2 networks.
Oh, right. Yeah. Yeah, that's super interesting. I was just wondering, because you've done it all for sort of a parametric normal distribution, but it kind of seems as though at least one of these parameters or a combination is like literally a temperature in like the statistical mechanical setting. And that might offer hints for like non-parametric or sort of different models. In the like the regularization coefficient for the variance is almost like a temperature term for an entropy, right? It's just a thought.
Yeah, and actually this project started when we were looking at temperatures and things in more of a Bayesian setting and then sort of morphed into this. So yeah, there's definitely connections there.
Okay, thanks.
Thank you. Great talk. So looking at your experiments, it seems that you are robust to your modeling assumption. In some sense, you start from a normal distribution. Maybe the previous question also elaborated on this a bit. So you start from a normal modeling assumption, but then when you do it to the normal data sets, like empirical data sets, you still have the same phase diagrams. So you say you are, in some sense, robust to this assumption?
I don't know if we have empirical evidence on these data sets we looked at that it seems to hold up, but I wouldn't go so, and we found it on every data set we ran it on actually, so I guess we're somewhat robust to it. It doesn't seem like it entirely relies on that.
Question on that? Oh. Oh, no.
I really like the talk, but I have a quick question about the parameter. So it seems like the rho and gamma still need to be tuned right, if I understand correctly. And you show that in this map, if the parameter lay in the phase S, the performance is the best, if I understand correctly. So that if you were say some mapping between the rho and gamma, so that you will only need to tune one hyperparameter. So kind of like this, or you need to search for the whole space.
Yeah, so that's what we're suggesting here in this drawing, is that instead of searching over the entire rho gamma square shown here, just look along this orange line. So it's now, instead of a 2D search space, we're looking at a 1D search space.
And you only look at the diagonal line, kind of like this.
Exactly, yeah. So that's what this plot is. This is that diagonal line, but I guess rotated.
Okay, got it. Thank you.
Yeah, let's take one last question. Yeah.
Thanks for the very clear presentation. When training your model is expensive, even that one-dimensional line search becomes costly. And my question is, how refined does my grid search need to be in the diagonals so that I don't overstep the phase S?
Yeah, we didn't look at that too closely, but what we did do when we did our search was I think we chose 100 points along this line, and we had them more densely packed on towards the corners, because that's where things are shifting quickly, because we're sort of dividing, if you look back at this slide. But I think sort of a rule of thumb that we found was that it's tended to be that this S zone was a bit lower. So you want a little bit less regularization on your mean, which sort of intuitively makes sense to care more about the mean being right. And it was almost always down more so than up in this corner. So if you wanted to be a bit cheap, you could probably start more in the middle here and go down that way. But as far as the density of these points, I don't really think I can give you a good answer for that.
Cool, fair enough. Thank you very much.
Okay, let's thank Elliot again. So with that, we conclude our first oral session. We're gonna go for lunch, but before that, let's give another round of applause for all our speakers. Lunch will be given in the same place as yesterday in the other building. Okay, see you around.
And also, let me say that if you have posters for today, you can already go to the room and try to hang them.